Hey all physics lovers, you know that in circular motion v vector is equal to omega vector cross r vector. But here this video I want to go to a much bigger thing from where this v is equal to omega cross r comes directly. And that bigger thing is the rate of change of a uniformly rotating vector. Hi, my name is Brajesh Chaudhary, your quantum guru. Normally we skip rate of change of a uniformly rotating vector in JEE syllabus, but we indirectly use that result. Here I'll directly derive that result, and using that result I'll plunge into a bit complex situation in which a body is rotating simultaneously about more than one axis, and then using this result we'll find directly the angular acceleration of that body. For that I'll take a question of Irodov, which we normally don't take for IIT-JEE syllabus, but here after taking this result we'll do it in a very straightforward manner. So let's go ahead. So I have this A vector which is rotating uniformly about z axis with a constant angular velocity omega. For the sake of simplicity, I am taking the vector A to be of constant magnitude. It is always at an angle theta with the z axis. Angular velocity is an axial vector, so direction of omega vector is along the z axis, i.e. along the axis about which this A vector is rotating. So I intend to find the rate of change of A vector with respect to time, and I want to find dA vector by dt. So let's see. So this is the situation at time t. You can see three vectors in the diagram. One is the omega vector, the angular velocity vector about which this A vector is rotating. A vector always maintaining angle theta with the omega vector, the magnitude of A remaining constant. And another vector is the red color vector, that is the position vector of the head of A vector, and the tail of that position vector r, the red color vector, is at the center of the circle. The circle at which the head of this A vector is moving. So this situation is situation at time t. After a very small dt letter, this is a new situation. Here is the vector A, direction has changed, the time has changed. Now this is at time t plus dt. So this change in A vector, magnitude remain constant but direction has changed, so A vector has to change. So change in vector is the new A vector minus the old A vector, so this is the dA vector. So as A vector is changed in a very small time dt, the r vector also changed. In fact, this r vector is rotating with the angular velocity omega. So now r vector has come here and r vector has rotated by angle d phi. Omega is nothing but the rate of change of this vector d phi with respect to time. And you know that infinitesimal rotations are vectors. So d phi is a vector whose direction is perpendicular to the plane of rotation. So this d phi is the purple color vector you can see here. So omega vector, the rotation of the A vector, the angular velocity of the rotation of vector omega vector is d phi by dt. And now you can see that right angle triangle, the radius of the position vector r, the length of the position vector r, or the radius at which the head of the vector A is moving is, say, small r. And from the geometry you can see that this small r is equal to A sine theta. A is the magnitude of vector A, which I have assumed to be constant. And we'll use a very simple result of the vector. Suppose a vector is rotating in a circle of radius r in a time interval in which it rotates by angle theta. The displacement of that vector becomes 2r sine theta by 2. So you can see that this position vector r is rotating. So by the time it has rotated by angle d phi, the change in position can also be written as r dA, because that is the difference between the two positions. So magnitude of dA from this diagram I can also write 2r sine d phi by 2. And now put the value of r, and we'll take the obvious approximation that the angle is very small and measured in radians, so sine theta can be written as theta. So using that approximation I can approximate magnitude of dA vector to be A sine theta d phi. And now I want to find the d phi cross A vector. So suppose this is d phi vector and this is A vector. The angle between d phi vector and A vector always is theta. So using the cross product, I can write the magnitude of their cross product is a sine theta d phi, and their direction. See, this is a vector, this is a d phi vector, this is a vector. So their cross product has to be perpendicular to this plane. So perpendicular to this plane mean it should be along this or along this. This is the plane of d phi and a, and the perpendicular to this plane is here or here. And then using cross product, and this is d phi cross a, so this is coming to here. So d phi cross a is along this direction, and that is the direction of dA vector. So I can say that the magnitude of dA is equal to the magnitude of d phi cross a, and direction of dA vector is the along direction of d phi cross a. So dA vector is d phi cross a. So if we differentiate this with respect to time or simply divide by dt, so we will get d phi by dt cross a, and you know d phi by dt is what? Omega. So dA by dt is omega cross a. So this is a general result for any rotating vector. The rate of change of a rotating vector is the rate at which it is rotating the omega cross that vector. So suppose now a particle is rotating in a circle of r, angular velocity. So what will be the, if we want to write v vector, we know that the v vector is dr vector by dt. So using this thing, dr vector by dt is omega cross r, and that is what we use in the circular motion. So now I want to apply this result in a complex situation. For that, I am taking this example of Irodov, a very good example. Question number 1.57 from mechanics part. Here you can see that a round cone with a half angle alpha, and the radius of the base is r. It is rolling uniformly on a horizontal surface. It is rolling and the center mass is rotating. So it is rolling uniformly without slipping over a horizontal plane as shown. The cone apex is hinged at the point O, which is on the same level at the point C. When the hinge point O and the center are on the same horizontal level. The velocity of point C is given v, so we have to find the moduli of the vector of angular velocity of the cone and the angle it forms with the vertical, and the velocity of the angular acceleration. So see, you can see that this is the center and this is the hinge point, and the center of the circle is rotating in a circle. The center of this cone and the hinge point O, they are separated by distance r cot alpha, and the center is rotating in this circle, horizontal circle, whose radius is r cot alpha. And as it is rotating, it has two angular velocity. One, if I look just the center point, the center is rotating in this, and the better word is the orbiting. So it has an orbital angular velocity omega o, which I have shown in the upward direction omega o, and it is rolling also this way. So it has another angular velocity, and that is called spin angular velocity. So it is rolling like this and center is moving like this, so it is moving like that. So that angular velocity is a spin angular velocity, and if I curl the right hand finger along the rotation, so thumb will give the direction of the spin angular velocity, and that is this omega s. And it is moving, rotating without slipping, rolling without slipping. When the point in contact with the ground has a velocity 0, because ground has a velocity 0. So this omega o and omega s cannot be unrelated. They have to be related by a direct relation. And directly using the concept of IUR, I can find the relation, and now I will find independently. You look the lowest point in contact. Lowest point in contact means this point, and this is r, this is v. So if I look this angular velocity omega s, so obviously omega s must be v by r. I think that should be clear. And if you look this velocity, and the distance from here is r cot alpha, so this omega o must be v upon r cot alpha. So these two things we've got. If I divide these two, so you will get omega O by omega S is tan alpha. Simple division. And the resultant of omega O and omega S is the omega net, because angular velocity is a vector, so resultant velocity is the sum of all the rotations, rate of change of rotations. So omega net is equal to omega O vector plus omega S vector. So I have drawn the omega net vector. And in the diagram also, you see that tan alpha is equal to omega O by omega S, that is I have written the. If you look more carefully, this omega net is along this slant length of the cone, and that I could have tell directly, because when a body has more than one rotations, more than one angular velocity, so you can look for the instantaneous axis of rotation. Instantaneous axis of rotation, the axis about which motion appears to be pure rotation. And to find IOR, what we need to look, just 2 points whose velocity is 0, and just join these 2 points. So see here, this point is in the contact of the ground. So obviously this point will always have a 0 velocity, and this is connected with this hinge point, this pivot point which is at rest. So this point has also velocity 0. So these 2 points have 0 velocity. So a line joining these 2 points would be IOR, and the net angular velocity will have to be along IOR. So that is one thing. Now, so that I could have directly get without calculation. Only one calculation was required, omega s. Then from omega s, I can directly get omega O, and from omega O, I can get omega net. So now from the diagram, I can say, from the diagram, you can say omega net is equal to omega sec theta, and omega s is equal to V by R. So this is a V sec alpha by R. And omega O, from the diagram you can see that is omega S tan alpha, and put the value of omega S V by R, so that is a V by R tan alpha. Now the most important part, the angular acceleration part, for which I am taking this question. So you can see that at a general position, so here I need to explain what I am taking. This is the center C. So here that center C, that is a time. So this is a R vector, position vector of the center C here. And so this is position vector of center C, and omega S is opposite to that vector at any time here. So now after time dt, the new position vector of R and the new position of the omega S vector are shown. So as the cone is rotating, you can see that omega O is not changing, omega S is changing. So in omega net, omega O plus omega S, it is omega net is changing because of omega S, spin angular velocity. And the spin angular velocity is rotating by the exactly same amount this position R is vectoring. And this rate of change of this omega R is actually, the rate at which this position R vector is changing, that is omega O. And the sense of rotation of R vector, and the R vector is rotating this way and the omega is rotating this way. So sense of rotation of R vector and omega S are the same thing. So omega S vector is rotating with an angular velocity omega. So this is a very good case. There are two angular velocities. One angular velocity is rotating with the other rate. So spin angular velocity is rotating with the angular velocity omega. Now it is a matter of a straightforward thing. Now angular acceleration vector. Alpha vector is the rate of change of net angular velocity. Net angular velocity is the sum of the orbital angular velocity and the spin angular velocity, omega O plus omega S, and out of these two, omega O is constant, omega is changing. So this is ds by dt. And I've just told that the d omega S vector is rotating with the angular velocity omega O. Just before we derived that the dA by dt is equal to omega cross A. There omega was the rate at which the A vector is rotating. So here omega S vector is rotating with angular velocity omega O. So dSO by dt is omega O cross omega S. So we've got omega alpha vector is the omega O vector cross omega S, and that is a very good case. And now we have to find the, so basically what I want, my intention is done. My purpose was to take a good example to illustrate that concept, that the dA by dt is the omega cross A. So here I have used ds by dt is the omega cross omega S. So using that thing, I have arrived to alpha is equal to omega O cross omega S. And now the magnitude of this alpha, you can see in this diagram, omega O and omega S are perpendicular. So magnitude of alpha is omega O into omega S. And we derive that here. Omega S is V by R and omega O is V by R tan alpha. So omega O into omega S becomes V by R whole square into tan alpha, and that is our answer to this very beautiful question. Thank you.